derive the Schrodinger equation in here. Let's go over the basics. A complex exponential equation, and it's in terms of the basically the wave function defines a wave function of a wave of a basically like it's basically wave functions. The square of a wave function like this squared is basically what enables you to find the operator. Squared is what enables you to find the probability density at a certain point of where an electron could be distributions. So let me tell you what it's like. Okay, so I'm going to be as fast as possible because I've noticed that it's pretty hard. This derivation is a little long, but it's simple. Okay, this is a constant which will be represented by the amplitude. This is iota, the imaginary unit, because our axes are like this is the imaginary axis, this is the real axis, and I guess this should be the complex axis, like the normal is going, or basically the variable which is moving, basically, whatever. So this is our, but we just ignore that for now. We're just gonna now go in the graphical part a lot. So we basically have to derive this thing first. This is not the first thing that we need to look at is the total energy is kinetic energy plus the potential energy of a system, and the total energy and the kinetic energy can be defined as half mv square momentum mv. How do you get them together? Okay, substitute this in here. Half m sorry, mv is already m and v are substituted, so we can say half pv. So v is p over m, so can we say half p square over 2m, sorry, over just m, and that gives us p square over 2m. So we can substitute the total energy as kinetic energy plus the V of x. V is the potential relative to a field. Potential energies are basically like to a field. Electric potential energy, elastic potential energy is not to a field though, but like the extension from a point. So there's no field. It's just field wells, something like that. Now, in order to look at these things, I need to know that the de Broglie wavelength is actually h over p. H being our normal Planck. Okay, so this is the sorry guys, this is the Planck's constant, and this is your momentum. According to Albert Einstein, the energy was basically light traveled in packets called quanta, and the energy in one packet is reduced Planck's constant multiplied by the angular frequency. Take angular and we talk about reduced Planck's constant. And reduced Planck's constant is a pretty simple thing. It's just the normal Planck's constant divided by 2 pi, which gives you the reduced Planck's constant. And that's what we use in general equations. And we also need to know that the momentum is the reduced Planck's constant multiplied by k, which is our wave number. Okay, momentum is basically your Planck's constant divided by the lambda if you take this. So can we say our wave number is like, I don't know, this thing, lambda over reduced Planck's constant, this would give us a 2 pi. So can we say our wave number is 2 pi over lambda? This is the wave number. This is just the derivations. This is not actually important for the real differentiation. In terms of potential energy operator, we can write this as x comma t, which is like the coordinates of space and time, and we can just write this as this. But what happens if we double partial differentiate in terms of x, right? So just take a off the thing. Okay, we don't need a right now. So I square n k square, I and k, I square k square, I square k square a. Basically this is the wave function. Now even if a is there, it doesn't really matter because this is this. We in substitution and we get minus k square wave function. Now we multiply the reduced Planck constant, the negative reduced Planck constant, squared on both sides. Now why do we do that? Well, it's just to get this form of the equation. So minus minus cancel, sorry. It's just reduce Planck's constant square, k square, and the wave function itself. Now when I divide by 2m here, you divide by 2m here. And what happens if we divide by 2m? H and k by the de Broglie equation, we knew h and k were p. So p square, p whole square, we just take this as p square over 2m gives us the kinetic energy operator. Okay, kinetic energy operator in terms of if we double differentiate it, double partially differentiate it, in terms of you can say x, basically the space vector, or space. What can I even say this one? Okay, but if we do it in terms of time, there's something you might notice that it's minus I w, the wave function, minus I w right here. If we multiply by I again and the reduced Planck's constant is actually important here. So we can get the reduced Planck's constant multiplied by W, or you'll say what happened to I? Well, can minus I be written as 1 over I because of the cycle? It's a long thing. My phone is literally just 1% charge. I can't explain all that, and maybe I'm not even gonna pull this with. I'm gonna just gonna say this. So we basically have the de Broglie equation is energy, and energy multiplied by the wavelength. So we have this thing. Basically, we have this thing, and this will give us the energy multiplied by this. Basically, give us the total energy, which is p squared over 2m plus v x lambda. This gives us the total energy. That just gives us kinetic energy. This gives us the total energy, and basically, what happened at that point was this thing for x and the potential energy separately, and this is what you get, like potential energy operator. Kinetic energy only for space, and total energy for time. Kinetic energy for space double. Okay, guys. I hope you got it. I'm gonna go more detail with the postulates and all those things, but right now